generally, the most general way that we started learning about this was covalent means a nonmetal plus a nonmetal. We ended up learning, as we went further along, that we wanted something with a low electronegativity difference. So when we took two compounds that were near to one another on the periodic table, as we know from the trends, if they're near to one another, their electronegativity values are going to be similar. If their electronegativity values are similar, the difference between the two elements would have a low electronegativity difference. Difference meaning subtracting the two from one another. It's not talking specifically about whether we're talking about pure covalent or polar covalent. It's just saying covalent in general, so sharing electrons. Just as a reminder there. On a side note, we remember that if we have a high electronegativity difference, so when we do our subtraction of the electronegativity values, and it's 2 or above, then we have an ionic, ionic substance, where they exchange electrons. So we are looking at the periodic table for which ones are close to one another. And we can see right off the bat that we have a metal and a nonmetal on very different parts of the periodic table when we have lithium and chlorine, so we can cross off that one. Phosphorus and oxygen, they're actually really close to one another. It's like, here's oxygen, here's phosphorus. So if we just look at the trends of electronegativity, they're probably going to be pretty close to one another, and they are, even if we don't have the electronegativity values. If we use our most basic definition from the very beginning of last school year, we have that nonmetal. So B should be the correct answer, but we always want to check to make sure there's nothing wrong with the problem or that there's not a better answer available. So we look at the last two. Calcium's a metal, sulfur's a nonmetal. They're far apart from one another on the periodic table, so we can cross that off. It'd be a high electronegativity difference. And zinc, even though it is a transition metal, it's still a metal. Bromine is a nonmetal. They're far away from one another, so we can assume that that is not our answer. So B was the correct answer for number 1. If you got it right, give yourself a star. If you got it wrong, fix it, make yourself a note so you don't get something like that wrong in the future. What questions do you have on that one before we look at number 2? So number 2. A solid with a melting point of 1,440 degrees Celsius. This is a high melting point. So we know it's solid at room temperature. Takes a lot to melt it. It is a conductor. Conducts both heat and electricity. And it does not dissolve in either water or organic solvents. We are looking for the bond between. So these are my intramolecular forces. Not my intermolecular, but my intramolecular forces, which means actual bonds. And then we look at all the different things that we have here. First of all, we see that covalent and ionic are my only actual intramolecular forces. The dipole and the metallic are kind of intermolecular. Metallic is a little odd. It can count both as inter and intra. It's not all nice and black and white for us, unfortunately. So we start pulling this apart. We need a high melting point. Covalents are generally low melting points, so we can cross that off right away. Dipole is an intermolecular force. It's keeping things that are generally covalent or polar covalent near to one another. It's not actually bonding them together. And so in that case, we can say, well, if it's mostly covalent, it would also have a low melting point, so we can get rid of those dipole. That leaves us with ionic and metallic. Let's look at the next part. Ionic will conduct heat and electricity, but only in a certain circumstance. Actually, two circumstances. What are those two circumstances where ionics will conduct electricity? If I take table salt. Go for it. Yes, absolutely. If it is in an aqueous solution, it will conduct. Or one other thing. We can make it molten. So if it's aqueous or molten, so we put it into the liquid form, which salts generally don't want to be because they have high melting points like this solid does. But it has to be aqueous or molten. And since it doesn't say in the parameters that it's aqueous or molten, it just says that it conducts heat and electricity, we can assume that it's not ionic. That leaves us with metallic. So let's see if metallic fits all of these things. We do know that metals have high melting points, generally. We do know that they're not going to dissolve in water or organic solvents. They may react with them, like sodium, the metal, that'll react with it. And it does, metals do conduct heat and electricity. So metallic is the correct answer, D for that one. Finally, question 3. We're looking for which one would include hydrogen bonding. Now remember that hydrogen bonding is not an actual bond, or not what we're talking about anyways. We're talking about the intermolecular forces holding bonded items together. So if I have a container of each of these, so a container of CH4, container of CH3COOH, container of CH3OCH3, it's asking which of those containers is having all of those molecules held together with hydrogen bonding, as opposed to dipole-dipole or van der Waals. Those are our only other two main options here. So we have to think of the parameters for hydrogen bonding. In hydrogen bonding, the actual molecule itself has to have a hydrogen that is bonded to one of 3 elements. It either has to be a hydrogen bonded to an oxygen within the molecule, and then the hydrogen bonding are the forces that are occurring between, or hydrogen bonded to fluorine, or hydrogen bonded to nitrogen. Has to be one of those situations. Now none of these have fluorine or nitrogen in them, so I'm going to ignore those for now. I'm going to think about this hydrogen bonded to oxygen. Well, in my first Roman numeral, CH4, the hydrogens are all bonded to carbon, so I can cross that off. So any one that has 1 in it, I can cross off. So theoretically, it should be A right off the bat. But let's double check, make sure that it was written correctly. I have CH3, C, double bond O, OH. That is my hydrogen bond that I wanted in my Roman numeral 2. Let's double check this last one though, because it has oxygens and hydrogens as well when I draw it out. My hydrogens are there with an oxygen but not bonded to it, and therefore it does not